So, what if I told you that our entire three-dimensional reality might just be an illusion? That everything you can see and touch and feel is actually a projection, kind of like a cosmic hologram that's being beamed from some distant, flat, two-dimensional surface. Now, I know that sounds like something straight out of science fiction, but it's a very real theory in physics that could completely rewrite our understanding of space, of information, and, well, of existence itself.
Okay, so to even wrap our heads around this, we first have to break an intuition about something that feels completely obvious. We all think that the more space you have, the more stuff you can pack inside it. But it turns out the universe plays by a totally different set of rules. The maximum amount of information a region can hold isn't determined by its volume. It's determined by its surface area. How on earth could that be right?
I mean, it just makes sense, doesn't it? A bigger warehouse holds more boxes. A larger library holds more books. For most of scientific history, this was just a basic, unquestioned fact about how the world works. Volume equals capacity. Simple. But the universe left us this incredible clue that our intuition was dead wrong. And that clue came from the most extreme, the most bizarre, and the most information-dense objects we know of, black holes. They were about to become the key to unlocking this whole mystery. So, this all kicks off with a simple thought experiment, one that just involves a cup of tea and a black hole. But it created a massive problem for physics. And this is really the moment where our entire picture of reality starts to unravel. Right, so back in 1972, a physicist named Jacob Bekenstein posed this really elegant puzzle. Imagine you've got a cup of hot tea. All those little water molecules zipping around chaotically represent a state of disorder, or what physicists call entropy. You can think of it as a measure of hidden information. You'd need a ton of data to describe the exact position and speed of every single one of those molecules. Now, what happens if you just drop that tea into a black hole? Well, it vanishes past the event horizon. The tea, and this is the crucial part, all of its entropy just seems to be deleted from our universe. And that, right there, is a universe-breaking problem. You see, the second law of thermodynamics is one of the most ironclad rules of reality. It says that the total entropy, or disorder, of a closed system can never go down. It's the reason eggs don't just unscramble themselves and why time only ever seems to flow forward. So if black holes could just delete entropy, this fundamental law would be completely broken. So this was the big crisis. It seriously looked like these cosmic monsters were violating a core principle of physics. Had we actually found a loophole that could, I don't know, reverse the arrow of time and completely break the universe as we know it? Well, Bekenstein came up with a really radical solution. He said, what if the entropy doesn't disappear? What if the black hole just absorbs it and its own entropy goes up? But where would all that information be stored? His guess was not in the 3D volume. He proposed that it was all encoded on the 2D surface of the event horizon. And that meant a black hole's information capacity is proportional to its surface area, not its volume. Now, a bold guess is one thing, but proving it is something else entirely. And this wild idea was about to be put to the test by one of the most famous physicists in history, who, by the way, was actually trying to prove it was wrong. You see, the great Stephen Hawking was deeply skeptical of Bekenstein's whole idea. It just seemed way too strange to be true. So he set out to put it to rest once and for all, using the powerful tools of quantum mechanics. He calculated what would happen to quantum fields right at the edge of a black hole, fully expecting to find a result that would end the debate. And what he found was astonishing, even to him. His calculations didn't disprove Bekenstein. They proved him right, and with mathematical perfection. He came up with this exact formula. A black hole's entropy, S, is precisely equal to its surface area, A, divided by 4. And the A here is measured in what are called Planck areas, which are like the smallest possible pixels of space that can even exist. The information was never lost. It was just painted on the surface all along. And that is the stunning takeaway, boiled down to one simple statement. For the most information-dense objects in the entire universe, the data describing everything that ever fell inside isn't stored in the 3D volume. Nope. It's written on the 2D boundary. The maximum information a region can hold is literally defined by its surface area. This shocking discovery about black holes then led two other physicists, Gerard 't Hooft and Leonard Susskind, to an even bigger, even more mind-bending idea. Not just about black holes, but about the entire universe.
See, their logic went something like this. Since a black hole represents the absolute maximum possible entropy for a given region of space, this rule must apply everywhere. And this led them to the holographic principle. What it says is that our entire three-dimensional reality might be nothing more than a projection of information that's encoded on some distant two-dimensional boundary or screen.
Okay, fine. But if that's true, what's creating the world that we experience every day? Why does it feel three-dimensional? When I look across a room, what is actually creating that sense of distance? Well, the answer, it turns out, is just as strange as the principle itself. The answer seems to be buried in one of the absolute weirdest features of quantum mechanics: entanglement. This is that spooky action at a distance that Einstein famously hated, where two particles become so deeply connected they basically behave as a single system, no matter how far apart they are. What happens to one instantly affects the other, even if they're on opposite sides of the universe. So there's this powerful idea that connects geometry and entanglement. It basically says that the fabric of our 3D space is literally woven from quantum entanglement on that 2D surface. Think of it like this. If two bits of information on that cosmic screen are highly entangled, they show up in our reality as points that are very close together. If they're only weakly entangled, they appear far apart. So in this view, distance itself, it's just a measure of entanglement. So what does this all mean for the world we live in? Well, if the universe really is a hologram, the implications are just absolutely profound. For starters, it suggests that our reality has a fundamental resolution limit. Because all the information is stored on a finite surface area, the total amount of information needed to describe everything in our observable universe is also finite. And believe it or not, physicists have actually calculated that number. It's roughly 1 followed by 122 zeros. Now, that number is almost incomprehensibly huge, but here's the key thing. It's not infinite. And that is the crucial insight. It means our reality basically has a data cap. There is a finite, limited amount of information that makes up everything we see and experience. And if information is finite, that means you can't just keep zooming in forever and ever. Eventually, you have to hit a fundamental limit. At the smallest possible scale imaginable, what's called the Planck length, our smooth, continuous reality would dissolve into discrete units, just like pixels on a computer screen. At its very core, reality is digital. All right, let's just pull this all together for a second. We started by seeing how our intuition is wrong. Information scales with area, not volume, a secret that was revealed to us by black holes. That discovery led to the holographic principle, the idea that our 3D world might just be a projection, where the very feeling of distance is woven from quantum entanglement on a 2D surface. And the final, absolutely stunning conclusion? Our reality isn't infinite. At its very rock bottom, it's finite, and it's digital. This theory gives us this incredible new picture of reality, one that is being tested and explored by physicists right at this very moment. It really does reframe everything we thought we knew. But it leaves us with one profound, ultimate mystery. If our universe really is a projection, then what and where is the screen?